Hello everyone, my name is Spaniol and I'm a master student at ISMO at Université Paris-Saclay in France under the direction of Olivier Pierali and Marie-Aline Martin. Today I will talk about the investigation of pure rotation of ethynylbenzonitrile isomers using chirped-pulse W-band spectroscopy. The cyanosubstitute molecule is a very interesting family for astrochemistry. Some of these cyanosubstitute molecules have been already detected in the interstellar medium. For example, the benzonitrile, the 1-cyanonaphthalene, and the 2-cyanonaphthalene. And some have been already studied by our team. For example, the phenylpropionitrile. When we look at the phenylpropionitrile, we also calculate the energy of all the isomers of the phenylpropionitrile. It appears that 3 of them, the 2-ethynylbenzonitrile here, the 3-ethynylbenzonitrile and the 4-ethynylbenzonitrile have energy very close from the energy of the phenylpropionitrile. So we decided to investigate the rotational spectra. So we start with the DFT geometry optimization harmonic to have the rotational constant of all these isomers and the dipolar moment. It appears that the 2 and the 3 ETB have a dipolar moment on A and B, and for the 4 ETB, a dipolar moment only on A. That means that we will have A and B type transition for the 2 and 3 ETB, and only A type for the 4 ETB. At ISMO, we have several techniques available, but today I will talk about the chirped-pulse millimeter wave spectrometer and the frequency multiplication-based millimeter wave spectrometer that we use to help during the exploitation of the spectra of the chirped-pulse millimeter wave spectrometer. We also use the room temperature flow cell. So just a quick reminder on the W-band chirped-pulse spectroscopy. It's commercial from widespec, and the frequency range is from 75 to 110 GHz. The transmitter is here. We have a cell here of 70 centimeters and the receiver. The sample is here and goes here to the pump. It's a sequential chirp with 30 MHz segment in the RGDR mode of widespec. We can record 1 million averages spectra within 2 hours, and we can choose a pulse length from 0.1 to 0.5 microseconds and the FED length up to 4 microseconds. So we record the spectra for all the ethynylbenzonitrile isomers with pretty much the same settings each time. So we have 1 million averages, a pressure around 1.6, 1.7, 10-3 microbar, a signal to noise ratio around 100, and a pulse length of 0.5 microseconds for the 2 and 4 ETB, and a pulse length of 0.25 microseconds for the 3 ETB. All the spectra are quite the same, but not exactly the same. We have small cluster of lines. And to explain how we exploit the spectra, I will focus on the spectra of the 4 ETB. We use 2 software to make the graphical exploitation of the spectra. We use Spectroscopy to modelize and fit the spectra using the set of constants, and LumiSmooth for Windows, the asymmetric top one from Lodiga, to make graphical assignment of transition. So how does it work? We had quantum chemical calculation that gives a set of rotational constants. We will predict the energy of rotational levels of the molecules with Spectroscopy. Then, in LumiSmooth, we predict the frequency of transitions between levels. We made the graphical assignment of the experimental frequency that we can see on the spectra to the transition, and we export the assignments. So we export the quantum numbers and the frequency. And then, with Spectroscopy, we fit these experimental observations to have a new set of rotational constants. And then we make iteration. So here's the window of LumiSmooth at the beginning. So you have segments of spectra one above the other. So here's the spectra of obtained with the chirped-pulse spectrometer, and here is the spectra obtained with the multiplication chain spectrometer. Each segment are 100 megahertz segments. So the frequency goes from here to here for the chirp, so 75 GHz to 110 GHz, and for the multiplication chain, 140 GHz to 220 GHz. Here's the quantum number J. So from 58 to 85 for the chirp, and 110 to 150 for the multiplication chain. We are focusing on the 4 ETBs, so there is only A-type transition, and we are looking at this transition. We are looking for lines aligned. Each triangle is a line, and the first alignment of lines is a bit away of the prediction. It's minus 250 megahertz from the prediction with the rotational constant obtained by the calculation. So we assign these lines to the transition, and at the end, when we have made some iteration, here is the result. So this is the first attribution that we have made for Ka0, and we can see the following transition for Ka1, 2, 3, 4, 5, and there is other outside the window. And so we have a pretty good rotational set of constants that give this simulation, and we compare to the experiment. We see that we are missing quite a lot of information on the experimental spectra. And if you look at Limiswood, we have a lot of lines not assigned and aligned. So that means the constant of the molecules that made these lines are pretty close to the rotational constant of the 4 ETB. So we thought it could be the first vibrational excited states. So we calculate with the DFT frequency calculation anharmonic the first vibrational states. So we have V26, 39, and 2 quantum in 26. And when we try to assign these lines to the vibrational states, here is the result. So in blue, all the lines, all the assignment is from the first excited states, V26. In pink, it corresponds to V39, and there is some here lines for 2 quantum in V26. And if we look at the simulation, we have a lot less information missing. So for the 4 ETB, we assign near 21,000 of lines for 4 states, the ground state and the 3 first excited states. We have an error in assignment around 0.046 megahertz. And if we look at the dispersion, for all states, we have pretty close the same dispersion, so our assignments are pretty good. For the 2 and the 3 ETB, we have a lot less lines assigned, around 5,000 for the 2 ETB, and around 15,000 for the 3 ETB. So because on the 2 it's still work in progress, and on the 2 ETB we are missing a part of the spectra from 160 GHz to 206 GHz. And for the both of us, 2 ETB and 3 ETB, we don't manage to assign the excited states lines. So In the future, we would like to assign the lines of the vibrational excited states of 2 and 3 ATB. And we can match already for the 4 ATB in stellar search because we have a very good prediction of the rotational spectra at room temperature for the 4 ATB. So we can make a good prediction for 10 Kelvin for astronomical, for interstellar search. I would like to thank all my collaborators and all the funding agencies.